I had a question yesterday from a student. That question was, when we're finding momentum, do we use an instantaneous velocity? That's a good question. Do we use an instantaneous velocity? That means the velocity at a specific moment of time. And the answer to that question is yes. Momentum is a quantity that exists either now or sometime down the road. It's a quantity that exists at a specific moment in time. Therefore, the velocity that we use is the instantaneous velocity, or the velocity at a specific moment in time. There is a way, however, to quantify momentum as it changes over time. It's not using strictly the concept of momentum, rather it's using the concept of impulse, which we define not as the momentum at a specific time, but rather as the change in momentum over a period of time. As an object gains or loses momentum over a period of time, we say that it experiences impulse. Now, because momentum is a vector and impulse is the change in momentum, we're going to say that impulse is a vector as well. It has a direction associated with it as well. We got to be careful with the sign of impulse, though. It can be a little bit tricky. It's a little bit harder than when we're talking about the sign of momentum, right? If something's moving to the right, we say it has a momentum that's positive. It's moving to the left, it has a momentum that's negative. Easy, right? Impulse is a little bit trickier. Impulse will be a positive value if the impulse is, let's say, in the context of north-south, if the impulse is to the north. The change in momentum is to the north. But when do we get an impulse or a change in momentum that is to the north? Well, if an object is moving in the positive direction and it gains momentum, it speeds up in the positive direction, then its change in momentum is to the north. Right? If it's moving to the north and it speeds up, its change in momentum is to the north, therefore we'd make the impulse positive. If it is moving to the north, but it's slowing down, it's losing momentum, then we would say its change in momentum, even though it's moving to the north, its change in momentum would be to the south. Does that make sense? So we'd make that a negative value. So we can get an impulse that's positive or negative, and that positive or negative on the surface doesn't look like it refers to a direction because we say it's a gain or a loss, right? But the gain or the loss really still does fundamentally refer to a direction. If you're moving north and you get a positive impulse, that means you're gaining momentum to the north. If it's a negative impulse, it means you're losing momentum to the north, or you could say you're gaining momentum to the south. Is that okay? Impulse is a vector. It has a positive value when momentum is gained in the positive direction, or it has a negative value when momentum is lost in the positive direction. We could just as easily say it has a negative value when momentum is gained in the negative direction, or it has a positive value when momentum is lost in the negative direction. All right, I want to relate this to Newton's second law now. If you remember Newton's second law from Physics 20, Newton's first law, object at rest stays at rest, object in motion stays in motion, straight line, constant speed, until acted upon by an unbalanced force. The third law was the action-reaction thing. If object A applies a force on B, B applies an equal and opposite force on A, or for every action, there's an equal and opposite reaction. The second law was basically F is equal to F times A. So I'm going to write that down. That's a mathematical statement of Newton's second law, but that's what we want to look at today. F is equal to m times A. Now, what I want to do is replace A with delta V over delta T. Can I do that? Is that okay? It's legal, right? All I've done is replaced the variable A with an equation that describes exactly the same thing. Now I want to rearrange it a little bit. Stick the T up by multiplying. I get F times T equals M times delta V. I just took the T up to the left side by multiplying because I didn't want it on the bottom on the right-hand side. Now, let me ask you this question, please. If I gave you an equation MV, not M delta V, just MV, what does MV represent? What is MV? You better be able to answer this question because we just spent 2 days on it. MV is, Caitlin? Momentum. Good. If MV is momentum, what do you think M delta V is? Or M times the change in velocity is? Yep. The change in momentum. Good. I'm putting this in a different color for a reason that you'll see in just a moment. Okay. Delta P, or the impulse, the change in momentum, is equal to M times delta V. But look what it's also equal to, F times T. If you take a step back from that for a second, it should make sense to us. If you want to change an object's momentum, question we had just a minute ago with the train moving to the right, slowing down. If we want to change that object's momentum, what do we got to do? We got to apply a force on the train, right? You got to apply a force. And the longer you apply that force for, the bigger the change in momentum you're going to have. You apply a force for 1 second, it changes the speed of the train. You apply a force for 10 seconds, it changes the speed and therefore the momentum of the train by more. So impulse, which is delta P, which is mass times the change in velocity, is also going to be equal to the force applied times the time over which that force is applied. Now, I want to refer you to your data sheet again. Everybody take out your data sheet. You're going to see why, when I do that, that I put delta P and the word impulse in a different color. We've already done this one, right? And we've seen this one quite a bit already as well. This is the new one that we've learned today. F times T is equal to M times delta V. On your data sheet, it doesn't tell you that that's delta P. It doesn't tell you that that's impulse. We know that it is. We know that that's the equation we just learned, but it is missing that variable. I wish they said delta P equals F times T equals M times delta V, but they don't. So we just have to be able to recognize that it is still delta P, or change in momentum. Now, what units, do you remember what units we used for momentum? Kilograms times meters per second, somebody said it there. And that was because it was mass times velocity, right? We can still use kilograms meters per second for impulse because it's M times delta V. But there's another set of units that we can also use for impulse, or even for momentum if we want. What is it, Cody? No, not joules times seconds, but you're close. Brianne? Newtons times seconds. Careful, we say, in both classes, period 1 and period 2 today, we said newtons per second. It's not newtons per second, because that would be N over S, right? Newton times seconds, or Newton seconds. These are interchangeable. Okay, these are interchangeable. 1 kilogram meter per second is equal to 1 Newton second. So use whichever one you want. You get an answer, okay, write down whichever set of units you want after that answer, because they're both correct. Just be familiar with both in case on a test, I give you one and not the other. So even if you have a preference as to which one you use, just be aware of the other one in case I don't use that one on your test. Let's do one example today and then we'll wrap it up. This example is the bottom one on the example sheet that I gave you on Wednesday. So I'm just going to ask you to copy out the solution, not the question itself. It says a 1,200 kilogram car is originally traveling 25 meters per second to the north. 35 seconds later, the car is traveling at 10 meters per second to the south. Oh, look at this. I got my blue pen in my hand. I'm going to put it down. I'm going to pick up my red pen. How come? What is it in this question that I think that I might mess up on if I don't draw attention to it? Damon? North and south. Okay, one of them is positive, one of them is negative. Usually you make north positive, south negative, although you could make it reverse as long as one of them is positive and one of them is negative. Let's write down some givens here. We know that this is an impulse question. Let's write down some givens so that we can solve it as an impulse question. Mass is 1,200 kilograms. My initial velocity is 25.0 meters per second. My final velocity is 10 meters per second. And my time interval here is 35 seconds. Is that good? Oh, what's wrong? Yep. That's why I saved a little space right there. It's because I need a negative in front of the 10. I'm looking for impulse, right? So I'm looking for delta P, the impulse. We know that impulse is equal to F times T, and it's also equal to M times delta V. Even though on our data sheet, it doesn't actually say impulse is F times T. It just says Ft is equal to M times delta V. We know that that's impulse. We know that that's delta P. I'm not going to use the F times T part of it, though. I'm going to use the M times delta V because I have mass and VF and VI. The mass is 1,200 kilograms. The change in velocity is negative 10 minus 25. And when I do that, I believe I end up getting negative 4.20 times 10 to the 4. We could say kilograms meters per second, or we could say Newton seconds. We got a negative value here, right? Which really means the impulse is to the south. You could think of it as a loss of momentum to the north, or you could think of it as a gain in momentum to the south. We were going north, now we're going south. We gained momentum to the south, or we lost momentum to the north. Now we want to find the force required to change the car's velocity. Let's say delta P is equal to F times T. Solve for force. It's impulse over time. It's negative 4.20 times 10 to the 4 over the time interval here of 35 seconds ends up giving me negative 1,200, or let's say negative 1.20 times 10 to the 3 newtons. Look at that, I ended up with the same value as mass. Is that a coincidence? Absolutely it is. Absolutely. I didn't even realize that when I made this question up. But now that I look at it, it's like, oh yeah, of course it is. What did I do here? I multiplied the mass by the change in velocity, which was neg 35. And then I divided it by the time, which was 35. It just happened by coincidence that the change in velocity happened to be the same as the time. That would be rare. Okay, don't expect to get the same answer there every time, because maybe 1 in 1,000 that would happen.